Okay, well, welcome back to our course on algorithms and data structures. We're continuing through some interesting material as we're getting through some of the basics of this. And so we have gone through the BAG. We talked about a couple different ways of doing implementation of that BAG structure with using arrays and using linked data. We also have had a couple of Java interludes as we're trying to give the context of implementing it into a specific language. Now we're going to be talking about the efficiency of algorithms in this lecture. So in this chapter, we're going to be introducing to terminology and ways that computer scientists use to measure the efficiency of algorithms. With this background, you will not only have an intuitive feel for efficiency, but also be able to talk about efficiency in a quantitative way. And so in terms of the textbook chapter context we'll be talking about, first of all, give a little bit of a motivation, talk about how we can be measuring an algorithm's efficiency. And then there's this one way of measuring complexity is something called the big O notation. We will have a little bit of a discussion on how you can picture efficiency, and finally looking at the efficiency of implementations of the ADT BAG, which is the first data structure that we are talking about in this course. So why do we need to be considering code efficiency? With amazing frequency, manufacturers introduce new computers that are faster, have larger memories than their predecessors, yet we, like various computer science professors, ask you to write code that is efficient in its use of time and space, which equates to memory. Such efficiency is still as pressing an issue as it was in the early years of computing, when computers were much slower and their memory size was much smaller. Today, the massive data sets we ask computers to process require us to maintain the same disciplines with efficiency. Efficiency remains an issue in some circumstances, a critical issue. So maybe we're able to process more data, but as the data analytics of a lot of areas are becoming more and more complex, and there's a huge exponential growth of data, where we're still getting to a point that efficiency is important. So here is some motivation for the importance of efficiency. Perhaps you think that you are not likely to write a program in the near future whose execution time is noticeably long. You might be right, but you're also that you are about to show some simple Java code that does take a long time to perform its computation. And so here you're just getting a chance to see some 3 different algorithms that basically does the same function of doing a summation. And you could see some radical differences in the amount of time it would take for them to process the results. So how you write your code is an important thing. So, quote, what is best? Usually, quote, best, the best solution to a problem balances various criteria such as time, space, generality, programming effort, and so on. The process of measuring the complexity of algorithms is called the analysis of algorithms. We will concentrate on the time complexity of the algorithm because it is usually more important than the space complexity. You should realize that an inverse relationship often exists between an algorithm's time complexity and space complexity. If you revise an algorithm to save execution time, you usually will need more space. If you reduce an algorithm's space requirements, it likely will require more time to execute. Sometimes, however, you will be able to save both time and space. Your measure of the complexity of an algorithm should be easy to compute, certainly easier than implementing the algorithm. You should express the measure in terms of the size of the problem. The problem size is the number of items that an algorithm processes. For example, if you are searching a collection of data, the problem size is the number of items in the collection. Such a measure enables you to compare the relative costs of algorithms as a function of the size of the problem. Typically, we are interested in large problems. A small problem is likely to take little time, even if the algorithm is inefficient. So here coming back to this simple summation, here we have counting basic operations and a comparison between these three things: the number of additions, the number of multiplications, divisions, and the total basic operations. And you can see there's a wide range of the number of operations that are going on. And so this next chart in a graph gives you an idea of the number of basic operations required for each of these three algorithms. And you can see how this algorithm C is going to perform a lot faster rather than these other ones. And so it makes sense that that probably would be a good approach for us to look at. And here's just give you accounting basic operations, a comparison as the number grows larger and larger. You can see that these numbers get quite huge depending on what is the type of operation you're accomplishing. So for some algorithms, execution time depends only on the size of the data set. Other algorithms, it depends on the nature of the data itself. So for some algorithms that operate on a data set, execution time depends only on the size of the data set. For example, the time needed to find the smallest integer in an array of integers depends only on the number of integers, not on the integers themselves. Finding the smallest of 100 integers takes the same amount of time regardless of the value of the integers. Other algorithms, however, have time requirements that depend not only on the size of the data set, but also on the data itself. For example, imagine that an array contains a certain value, and we want to know where in the array it occurs. Suppose our search algorithm examines each value in the array until it finds the desired one. If the algorithm finds the desired value in the first array element it examined, it makes only one comparison. In the best case, the algorithm takes the least time. The algorithm can do no better than its best case time. In the best case time, if the best case time is still too slow, you need another algorithm. Suppose that the algorithm locates the desired value after comparing it to every value in the array. This would be the algorithm's worst case since it requires the most time. If you can tolerate the worst case time, your algorithm is acceptable. For many algorithms, the worst and the best case rarely occur. Thus, we consider an algorithm's average case when it processes a typical data set. The average case time requirement of an algorithm is more useful, but harder to estimate. Note that the average case time is not the average of the best case and the worst case times. So now we get into this big O notation. And so computer scientists use a notation to represent an algorithm's complexity. For example, consider algorithms A, B, and C that we have already talked about for the basic operation that each requirement is shown. Instead of saying that algorithm A has a time requirement proportional to n, we say that A is big O n. We call this notation big O since it uses the capital letter O. Algorithm C requires three basic operations, regardless of the problem size, and this algorithm requires at the same time, we say that algorithm C is big O1. So that's definitely a better approach. So here we just show a graphical illustration of the value of the function in the formal definition of big O. And so here is just some examples of big O notation and some of the identities that are associated with them. If you're using a couple algorithms, a way that you can do algebra, putting those together. Here's a way of picturing efficiency. Much of an algorithm's work occurs during its repetitive phases, that is, during the execution of the loops, or as we'll see in chapter 9, as a result of a recursive call. So we're just showing some more examples of that here. So that this first one was for an algorithm of a big O n. Here is it for a big O n squared. And here is just some more details of that. And we can also start to be looking at efficiency, the effect of doubling the problem size on an algorithm's time requirement. And here we're seeing how that starts to play out based on different types of things that we could be doing. And just to follow on, here's the time required to process 1 million items by algorithm of various orders at the rate of 1 million operations per second. And you can see how some of these things are small and some of them are incredibly large. You know, these numbers are just unfathomable. So you can see how it can make a big difference. All right, here is how we can be comparing the implementation. So using big O notation, in this table, we're summarizing the time complexities of the operations of the ADT bag for implementations that use a fixed size array and a chain of link nodes. For some operations, multiple time requirements indicate the best, worst, and average case. And so here we have two different approaches, and we're seeing the difference. And so this could be one of the ways that you would be using to determine one implementation versus another. Okay, that's it for this chapter. Thank you very much.